Hello, everyone. Welcome to today's episode of Meet the Young Professionals, where we invite the young professionals who were once part of the IEEE Bangladesh section or Bangladesh and now move to different part of the world for their career. And I'm extremely honored today to have Dr. Shehrin Sayed as the speaker. Dr. Shehrin Sayed completed his B.Sc from Bangladesh University of Engineering and Technology, and then he completed his master's and Ph.D. in ECE from the Purdue University. He's currently working as a postdoc researcher in the Electrical Engineering and Computer Sciences Department at University of California and the Material Science Division of Lawrence Berkeley National Laboratory. His research interests include non-volatile memory, magnetism, and spintronics. And he's currently working with another former member of IEEE Bangladesh section, Dr. Saif Salahuddin, who's currently a professor at UC Berkeley. So without further ado, I would like to give the floor to Dr. Saif to give his talk on spintronics.
Thank you, Sajid Bhai, for the wonderful introduction and also for the invitation. I'm happy to be here. So let me share my screen. All right, so hello everyone, I'm Shehrin Sayed. I'm a postdoctoral researcher and jointly affiliated with Electrical Engineering and Computer Science at UC Berkeley and Material Science Division in Lawrence Berkeley National Lab. And I'm working on various projects in between these two campuses. But today I'm not going to talk about any particular project, but Spintronics research in general. I'm going to start with the big picture. What are the major challenges and we are facing in technological advancements? And then I'm going to discuss how Spintronics has been playing a role in addressing some of these challenges. Specifically, these new discoveries was translated into new technologies at various times, which had a tremendous influence on our lives. And I'm going to end with a future direction. Before I start, let me quickly mention that we recently wrote a nanomagnetics ebook from UC Berkeley, and our target audience was high school students. So this book is very easy to follow. So if you are interested in fundamentals of spintronics, you can look up this ebook online on NanoHub. So let me turn off my video so that we all have good internet speed. Okay. So electronic data, which is the most valuable thing in today's world. And we are producing a high volume of electronic data every day. And the source of electronic data can be as sophisticated as experiments on Large Hadron Collider that requires large-scale data centers for storage, typically known as the core source of such data generation. Or it could be as simple as taking selfies for your Instagram. So we are generating electronic data in various ways. And right at this moment, we are generating electronic data over this video call. And I guess some version of this talk will be uploaded on YouTube. So more data is good. That means more fuel for the data-driven applications we have been hearing about. For example, big data analytics, machine intelligence, and all these exciting applications. But let's see how much data we are about to handle. On this, International Data Corporation, in collaboration with Seagate, published this white paper in 2018. And there, they have quantified the data captured, created, and replicated in any given year across the globe. Currently, we are here. So this y-axis, the unit is billion terabytes. Billion is 10 to the power 9. And terabyte, we are all familiar with what terabyte means. Currently, we are here around 50 billion terabytes. So this was an estimation from 2010. I'm pretty sure the number is much higher because due to the pandemic, everything is online. But based on how we have scaled in the past, they have forecasted that within the next 5 years, we will produce 175 billion terabytes. And this is a big number. What this means is that we will produce this amount of data just in the year 2025. And the big question is whether we can store at least a major part of this data. Can you see this large, small red bar here? That's the installed storage capacity worldwide. And it's roughly around 6.8 billion terabytes. Interestingly, 65% of it is hard disk drives. And this is where Spintronics has been playing a role, which I'll discuss a little later. But you can see the gap between how much data we are generating and what's our storage capacity. And going from here to there, like within the next 5 years, we need to significantly enhance our memory capacity. So this is one of the major challenges we are about to face. The second challenge is that we want to analyze the data, right? Because at the end of the day, we want to process the data, find patterns, or make decisions out of it. So we need processors. And our processors are quite fast, even like in your personal computer, your processors are very fast. And clock cycle, like if you round it up, it's roughly around 0.3 nanosecond. But for computation, your processor needs to talk to various levels of memory. And the fastest memory are the cache memory, consists of SRAM, which is very fast. Within 3 cycles, you can collect the information. But our working memory is DRAM, which takes more than 100 cycles to communicate with the processor. And in between, your processor is just sitting idle. And these are all volatile memories. That means if you turn off the power, your memory goes away. That's why you need a non-volatile storage. And that's pretty slow. Even if you use solid state drive, that takes 150,000 cycles to communicate with your processor. So there is a huge gap between the processor speed and the memory speed, which needs to be overcome if we want to enable all the exciting data-driven applications. One good example could be this autonomous vehicle, which is expected to generate 1 gigabyte per second. And this number will keep growing as things are advancing, but your vehicle needs to process a large amount of data within a fraction of a second and make decision out of it. So your memory needs to be much faster so that you can drive safely. Third major challenge is the energy and environmental aspect. So this is a report from Climate Change News, which was published in 2017. And the high data generation rate, they're calling it tsunami of data. And it's about to consume 1/5 of global electricity within next 5 years. And it is expected to contribute to 3.5% of the global carbon emission. So these are all bad for environments. Later next year, like a publication, an article on Nature said, okay, these numbers are okay, but we won't see them within next 5 years, but 10 years. But still, 10 years not far away, and we need to do something so we don't go there. 20% of the global electricity is a large amount of electricity. And you know, like electricity means I square or dissipation. So things will heat up. Even today, heat management in data centers are quite challenging and very expensive. And one of the best solution for heat management is just cooling with water. And this is not a joke. So I'm showing you a news that from 2018. So Microsoft is deploying an underwater submarine-like data center to boost the internet speed. And their idea is that like the natural flow of seawater will cool things down and they can cut down the cost of heat management. So don't get me wrong, this is a beautiful project with lots of promises, and this data center runs on renewable energy. So I think this is the phase 2 of the project, and they deployed it around 2018. And sometime this year they took it out and it looked like this. So cooling with water is fine, but what this tells me that there is an enormous opportunity to find new materials, translate into new devices and applications to address some of these global issues. And these are global issues. It's like world hunger. Like there is no single solution to a global problem. So various people are doing various things. For example, some people are trying to scale the solid state devices, like 3D integration. Some people are looking into new materials, for example, ferroelectric memories, resistive RAM, and phase change materials, all these things. But today I'm going to talk about a specific field of research, which is spintronics, and how, like at various times, new materials and physics was translated into devices that address some of these issues. So what is spintronics? We are all familiar with conventional electronics, which is based on like charge property of electrons. And the electronics is basically the physics and mechanics of electrons in solids, right? So a macroscopic property that we see in solid is the conductance, which is proportional to your charge density. So N is the carrier density or electron density, and your conductance is proportional to that. And now we have transistors, so we can apply a gate voltage and change the number of electrons and change the conductance accordingly. So more electrons means logic 1, less electrons means logic 0. And that's how whole digital electronics is built on. So short version of what spintronics is that we are using another property of electron, which is its quantum property spin. It represents its angular momentum. So angular momentum can be this way or that way. So we call it, it can be up spin or down spin or any superposition of these two. And the macroscopic property we can see in materials like magnetic materials as magnetization. So we know that magnet tends to point in certain direction, right? So what that means, like majority of the electrons are pointing in some direction. Their spin is pointing in some direction. And we can flip the magnet, let's say south, north to north, south. And that means like we just change the majority spin type. That's it. And how do we switch from 1 to 0? So let's call this 1 and let's call this 0. And how do we switch from this state to that state? We can apply an external magnetic field. And this is a well-known MH loop. We can apply, so suppose we are here, we have a state 0. We can apply a positive magnetic field, and if our magnetic field is higher than the switching field, then we will switch it to 1. And if we remove the field, it will stay 1. And that's why we see this hysteresis. That means this hysteresis represents the memory within the magnet. Okay, so please feel free to ask questions anytime during the talk. Just unmute yourself and ask questions. So what separates 0 from 1? So there is, if you look at the energy diagram between the two states, 0 and 1, 0 and 1 are equal energy states, because this is the potential energy and we are not changing the total number of electrons. So potential energy doesn't change. What we are changing is the collective spin direction. And these two states are separated by a large energy barrier, which is called the anisotropy energy barrier of these magnetic materials. It's defined as half ms hk and sigma. Sigma is the volume of your magnet, ms is the saturation value of the magnetization, and hk is the field at which your magnet switches. So this defines your barrier height. And that barrier height determines the memory retention time. What that means, like how long your memory will be there. Like if you store some information in your magnet, how long it will stay there reliably. And magnets are very reliable. Like this tau naught is a material parameter. This Kb is the Boltzmann constant, T is the temperature. So at room temperature, this tau naught is roughly around 1 picosecond, but since this barrier height goes into an exponential, even a 60 kT barrier height gives you a number as big as 1 billion years. 60 kT is the number typically used in industry magnetic bits. But in real life, things won't be 1 billion years. It will be a more realistic numbers because you have a Gaussian distribution due to the process variation. But it is well known that magnets are a reliable storage device, can make reliable storage device. So I'm not sure anyone of you will recognize this, but this device was very popular when I was in high school for listening to music. It's called cassette. And to play this device, we needed, like, this was like the iPod of my generation. And last year I was visiting Bangladesh and I found one of these from my high school, and surprisingly it still works. Although the sound was noisy, I wasn't sure whether it's the problem of the storage or this device, but this kind of tells me like how reliable magnetic storage can be. But this is more on the analog recording side. I'm going to talk about the digital recording side. So magnets have been scaling our storage memory capacity in the form of hard disk drives. It started around 1956. So this is the bit density of our hard disk drives and as a function of year. So it started around 1956. Do you see this large thing here? Looks like a large refrigerator. That's the memory device back, like it started with IBM. And it could only store 4 megabytes of data. And over the time, various new discoveries and materials came and scaled our capacity and make things much smaller. And it scaled by like our capacity was enhanced by 1 billion times. And I'm going to just discuss a couple of important discoveries. The first one is giant magnetoresistance, around 1988, discovered by Albert Ford and Peter Grunberg. What this phenomena is, like if you have two magnets, let's say this is a magnet and this is another magnet, these are separated by a thin metallic spacer. In between, you have a metal and you have two magnetic layers. So this is a two-terminal device. And if you look at the two-terminal resistance, then the resistance will be high when the magnets point in the opposite direction. It's called the anti-parallel state. And the resistance will be low if they point in the same direction. It's called the parallel state. And the change between anti-parallel to parallel, back then it was around 5 to 50%. And it was giant compared to what people knew back then. That's why they named it giant magnetoresistance. And the fact is that always anti-parallel resistance is higher than the parallel resistance. It was commercialized, so it became a device called spin valve, and it was used as magnetic read head in hard disk drives. And it was commercialized around 1997, and it scaled because we could make the device much smaller, it scaled our density by 3 orders of magnitude since its discovery. And it made a big difference in terms of our storage capacity. That this discovery won 2007 Nobel Prize in Physics. Later, people realized that if you replace this metallic layer with an oxide, specifically magnesium oxide, you can further enhance your magnetoresistance. And it was predicted by Butler and Mason around 2001. And later it was demonstrated around 2004 by Stuart Perkin. But the demonstration was around 200%. But this is like much larger than the giant magnetoresistance. But since the word giant was already taken, so they named it tunnel magnetoresistance. And this device was called magnetic tunnel junction, which was commercialized at the Reed Head around 2006, and further scaled the density by another three orders of magnitude. And these are very important discoveries because these enable the tools for like various new applications like social media or like streaming services. All these things like online shopping, everything became possible because we were able to scale our capacity. And this discovery was awarded the 2014 Millennium Technology Prize. And this is a prestigious prize. The first person who received this invented internet. So this is like the prize is given based on how your discovery has affected the humanity. Okay, so this is the story of hard disk drives, and the future, like there are many ongoing efforts in both academia and industry. Let me just mention one of them. Like Western Digital is promising 4 terabyte per inch square by 2025, and one device is expected to store 40 terabytes. And this is based on a new effect, which is this microwave assisted magnetic recording. And this is under development. One important thing that this small device, we can scale it down, make it small, and the device switches much faster. So people quickly realized not only storage, we can use it for random access memory because it switches fast and we can scale the device. And in the earlier days, people used to switch the free layer. Like there's a reference layer and the free layer. The free layer is the storage where you store your information. And in the earlier days, people used external magnetic field to switch it. And to generate that magnetic field, they just run a current through a wire. And by Ampere's law, you generate a magnetic field. So this is the right-hand rule. If your thumb is pointing towards your current direction, your other fingers are pointing towards your magnetic field. And if you reverse the current, the magnetic field reverses as well. So you can apply a large current and create the switching field and switch the free layer. And for readout, you'll be looking at the magnetoresistance. And it's quite interesting for embedded application because the density scaling was very hard because you need very complicated circuitry to generate the magnetic field. And also like when there was a selection problem because when you're trying to switch one bit, it's easy to affect the other, like what's surrounding it. So there are some problems, but recent MRAM technology is based on this spin transfer torque physics, which was proposed by Slonczewski and Berger in 1996. And what they say, like, okay, so you can apply a small current and read out the resistance for readout, but if you increase the current and at a large current, it will just switch your free layer by applying the spin transfer torque. And if you reverse the current direction, your bit will flip in the opposite direction. So your switching is reversible. So let's look at the anatomy of this new mechanism. So this terminal, the reference magnet is connected to one of the battery terminals, and it's injecting an unpolarized current. By unpolarized current, I mean there are equal number of upspin and downspin, so there is no net spin polarization. So the top magnet is a reference, so it acts like a polarizer. So when electrons pass through this magnet, a portion of it will get polarized, and there will be an efficiency factor. So now you have spin polarized current because this one acted like a polarizer. And this spin polarized current is now transferred to the storage magnet. So let's say one downspin electron comes to the storage magnet, hits the equilibrium spin. So these are all equilibrium spin and these are non-equilibrium spins. The difference is that these are within the material and it stays there even if you turn off the voltage, and these are induced by applying a voltage. That's the difference. So one non-equilibrium spin comes, hits one of the equilibrium spins, there will be an angular momentum conservation. So now this one will become downspin and this one will become, this one will become upspin and this one will become downspin. And if you hit the magnet, the storage magnet, with more spins, you will flip more of the spins inside the magnet. And these electrons then go away to the other terminal of the battery. And if you keep hitting your storage magnet with more spin polarized current, at some threshold value, you can switch it. So that's the basic of the spin transfer torque. And all the major industries are currently developing this technology, and it's quite promising to, especially for embedded application, and it's quite promising to replace the low density SRAM and DRAM at this point. But as I mentioned, one major thing is that we need large current to create, large unpolarized current to create a substantial spin polarized current. So that's one of the major problems right now. So this is a data from IBM from last year's IEDM. So they demonstrated like an MTJ, which was diameter around 50 nanometer, quite small. So this is promising for density scaling. And their write current was around 159 microampere. And switching was very fast, just a few nanoseconds. But if you translate this current into a current density, it is 10 to the power 7 amp per centimeter square, and that's quite large. Specifically, it creates some reliability issues because, as you remember, we have an oxide in between, and that oxide is very small, like thinner than 1 nanometer, and it creates reliability issues in terms of breakdown. Other than that, large current creates dissipation because this is a resistive element, so I square R is large, and that translates into large write energy. So on this plot, I'm showing various random access memory technologies, their energy and delay. So these two are SRAM and DRAM, which are volatile, and all the other data points are non-volatile. So compared to other technologies, STT MRAM is quite fast. But due to this large write current, the energy for switching is very high. So we need to lower the write current because at the end of the day, we want to bring it closer to what we observe for SRAM. Another problem associated with this large write current is like we're running the current through this device, but in a large array, we need to select a particular bit. So we need a transistor, and that transistor, the same current will flow through this transistor. And the best transistor can give you an on current per unit width, which is like 1 milliamp per micrometer. And like the same in different units, like 1 microamp and nanometer. So you can see, to accommodate this write current, your transistor width has to be greater than at least 159 nanometer, right? Because your write current is 159 microampere. So even though you can make your bit size closer to 50 nanometer, and these days people are scaling it much lower, like even 3 nanometer diameter has been discussed. But the problem is that the write current is very high, and for that your transistor size has to be high, so your cell size is high. So that kind of stops you from further density scaling. So let's look at the physics, like what's stopping us from lowering the write current. So as I mentioned, like for STT, you need to have at least a minimum amount of spin polarized current to switch it. And that threshold value is given by this expression. It depends on the anisotropy energy, which separates the 0 from 1. And for a particular technology, so this determines your memory retention time. So for a particular technology, this is fixed. You cannot change it. So only parameter that you can play with is this damping factor. So it's a parameter that determines how your magnet switches. But as you lower the damping, your delay is inversely proportional to the damping. So if you try to lower your energy, you make the device slower. So that's there is a trade-off between threshold and delay. And in addition to that, like to create a spin polarized current, we need to apply a charge current. And as I have mentioned that there is an efficiency factor, which is lower than 1. So you're losing something here as well. So that's why our write current is very high. So what we can do, we can try to find new materials and phenomena to lower the current, or try to come up with a new voltage control device. So let me first talk about a different type of MRAM. So that utilizes materials with spin orbit coupling. Spin orbit coupling is a relativistic effect in solid. What happens if you run a current through this material, you have a spin polarized current in the transverse direction. And this is different from the STT because you run a current in this direction, your spin polarized current is also in the same direction. It was polarized by the top magnet. But here we are utilizing a different effect. Some people like call it spin Hall effect, and there could be other origins for that. But the fact is, like if you run a current in one direction, you will have a spin current in the transverse direction. So if you have your MTJ right on top of it, you can switch this free layer, and that's reversible because if you reverse the current, your spin current also reverses. So there are a few benefits, like in STT, spin current is proportional to the charge current, and there is an efficiency factor that's less than 1. But now your charge current and spin current are in two different directions. That's why you like pick up a geometric factor, which can be much greater than 1. And also there is this efficiency factor, which is supposed to be the property of this material. This can be greater than 1 as well. So overall, this coefficient can be much greater than 1. So we can create large spin current for a given charge current. So let me just explain the physics in simple terms. What's happening? When we drive a current, let's say in the forward direction, we create a spin accumulation in this kind of material. And the origin of spin accumulation can be bulk spin Hall effect or some interface effect like Rashba. So this is still being debated in the field. Like some people are saying it's bulk, some people are saying it's interface, and some people are saying it can be both. But let's treat it like a black box. If you run a current, you create a spin accumulation of non-equilibrium spins. And by non-equilibrium, I mean like if you turn off your voltage or current, these spins will go away. And spin accumulation, the majority spins like are, let's say, up, and minority spins are down. You know, when you have a collection of electrons, you have a potential, and now you have spin polarized electrons, so you have spin potential. Since like majority spins are high in number, the majority spin potential will be higher and minority spin potential will be lower. And in this gap, like the difference is called the spin voltage, and that's constant along your channel, constant across your material. And if you reverse your current direction, you just change the majority spin type, right? So that's why now your red curve is higher than the blue curve when you reverse your current direction. And that's why you can inject different type of spins into your MTJ for switching and create this new type of MRAM. So one interesting thing that since these are potential, we should be able to measure it, right? But for that, we need a spin selective contact, and magnetic contacts are quite spin selective. If you have a magnet that's aligned with the majority spins, it will measure this blue curve. And if you reverse your magnetization, and now it's aligned with the minority spins, it will measure this red curve. So this was a prediction from our group at Purdue. And what we said that like we should be able to measure this in terms of a voltage. So for two different magnetic state, the voltage will be different. And it was later demonstrated experimentally on topological materials called bismuth solenoid around 2014. So in this experiment, they are measuring the voltage for a given current, and the current is around 2 milliampere. This current is fixed. All they're doing is applying an external magnetic field and switching this magnet. And for the two different magnetic states, they observe two different voltage, which corresponds to this blue and red curve. And the difference between them is called this spin voltage. And later, many other materials, like this phenomenon was observed in many other materials, like diverse classes of materials that includes topological materials, condo insulator, semiconductor, metals, mostly heavy metals, and then semi-metals. If you take all the measured data from different groups at different times and look at the spin voltage for the given current, and then multiply with the width to make each of the data points independent of the sample width, and now you have a unit of resistivity. Then what we observed that all these measured data are following a trend like that is inversely proportional to the density of states of your material. And that was another major conclusion of our theoretical model. And all these experiments are following that theoretical prediction. So what this tells you that if you have a material with lower density of states, your spin voltage will be larger, and that have the potential to lower down the right current. So we are interested to lower the right current. Okay. This is interesting because we know various tricks to tune the density of states. For example, we can apply a gate, apply an electric field to change the density of states, or we can look into various oxide material. For example, right now I'm collaborating with material science department to look into oxide materials that have the potential to change the density of states by strain modulation. So there are many things we can play with from material science point of view. Another thing I want to show, so this is another prediction from my PhD. So now let's think about the same thing, but with two magnetic contacts. So let's keep the current that's flowing in the spin orbit material fixed. When both the magnets are in up direction, both of them will probe this blue curve. And the voltage difference will be just this offset voltage due to the ohmic drop within the channel. If you reverse both of them, like now both of them are in the down direction, and both of them will measure this red curve and measure the offset voltage. So these are parallel states and they are equal. But let's look at the anti-parallel states. When the left one is up, right one is down, left one will measure this blue curve, right one will measure this red curve, and the voltage difference will be this offset plus the spin voltage, this difference. If you look at the opposite case, where the left magnet is down, right magnet is up, now this left magnet will probe the red curve and the right magnet will probe the blue curve, and the voltage difference will be offset minus the spin voltage. So these two are unequal. So the anti-parallel states become unequal. So how do we see that experimentally? We can make one of the magnets much bigger than the other so that when we apply an external magnetic field, one of them switches faster than the other. Like one of them switches earlier than the other, not faster. Thus, we can see all possible states, like they can be both down, they can be both up, or down up, and up down. And what we are expecting that the parallel states are equal, but the anti-parallel states are unequal. One of them is lower than the parallel states, and the other one is higher than the parallel state. And this is observed in multi-terminal setup. So two major things about this prediction is that we will have anti-parallel states. This is like symmetric around the parallel states. And another thing is this effect is supposed to be long range. Like if we separate the distance between the contacts, this signal should not degrade because this is a new physics. And this is way different than the conventional magnetoresistance, where I have mentioned that anti-parallel states are always higher than the parallel states. And this signal persists like only up to few nanometer of separation between the contacts. So we predicted this around 2016, and later it was demonstrated on indium arsenide by our collaborators in Korea, Institute of Science and Technology. And they have demonstrated these unequal anti-parallel states at room temperature, and they like shifted the contact from 5.9 micrometer up to 1.62 millimeter, and that's very long distance, and the signal did not degrade at all, which was one of the major conclusion of a theoretical model. So this physics is very interesting. Like physics is always interesting, but as an electrical engineer, we always want to use this new physics and engineer into devices. So we have proposed, like since this is a new type of magnetoresistance, the conventional magnetoresistance like was used in memory applications. So this new type of magnetoresistance we can use in magnetic tunnel junctions. Like, we can use without magnetic tunnel junction, like we can propose memory device without magnetic tunnel junction. The second thing is in computation. The Korean group who demonstrated this phenomena experimentally, they also demonstrated a reconfigurable logic gates. Like this is very interesting because like you can design a circuit that changes like based on what information you store inside it. And it could be very interesting for in-memory computing, like your memory will compute for you. And third application could be on the analog side. So we have recently proposed a rectifier. We call it the spin orbit torque rectifier. That can be used for RF detection and energy harvesting, but from very weak signals where conventional technologies do not operate. So I wanted to show you these references in case you are interested, but I'm not planning to talk about it today because I want to talk about the last part of my talk, which is a voltage control device. So to address the problems we have, we need to reduce the current in existing MRAM technology. So either we can find new materials that will lower down the current, or you can find a voltage control device. And many people are proposing various types of voltage control device. And from Berkeley, we recently proposed a new device. But before describing that, let me explain a phenomena which is called this exchange coupling. And it's observed in spin valve. If you remember that spin valve means like two magnets separated by a thin metallic spacer. And the experiment that was observed around 90s, like they just increased this metallic spacer thickness, and at equilibrium these two magnets periodically switch from anti-parallel state to a parallel state to anti-parallel state again to a parallel state. And that was quite amazing. Like it's happening at equilibrium, and when you're changing just the thickness of the middle layer. And it's observed only for like transition metals, like when your metallic layer is a transition metal like ruthenium, rhodium, iridium, and there are other materials like copper. I haven't listed all of them. But soon people realized this phenomena can be explained with the wave nature of electrons. That means like this is a quantum phenomena. And the coupling stays like, you can switch with an external magnetic field, but something is holding them together to make either anti-parallel or parallel. Because as soon as you remove that field, they turn back to their original state. So there is a coupling energy associated with it that's periodic in nature. And the physics is quite simple. We have electrons, equilibrium electrons inside the magnet, and they are spin polarized. So we have a spin dependent wave function that can go from one interface to the other. This one get reflected, come back, and creates an interference pattern, just a wave interference pattern. So you will have bright spots and dark spots. And when you're changing this middle layer thickness, you're basically changing the interference pattern. That's why you're seeing a periodic nature. So this is the bright spot, dark spot, bright spot, dark spot, and the magnets are changing accordingly because you're actually changing the density of states. And it was theoretically explained very well in this paper. You can look it up if you're interested. So what we are proposing, so we want to engineer this phenomena into device. So we added two oxide layers. When you have large oxide layers, you have large barriers. So wave function cannot travel from left to right anymore because a large barrier is kind of diminishing it. But since you have two barriers in between, you have a metallic layer, and if you choose the right materials, you can create a quantum well in between with discrete energy states. This is very interesting because now you can apply a voltage across the structure, and what that voltage will do, it will change the quasi-Fermi level of your contact. And when your quasi-Fermi level is at one of these discrete states, the transmission coefficient between left and right becomes very high. And that is very well known as resonant tunneling. So now your wave function from left magnet can propagate to the right magnet and come back and create that interference pattern. So that was our hypothesis, and we did like sophisticated NEGF based quantum transport simulations to test our idea, assuming realistic materials parameter. And what we found that yes, it's possible to induce a voltage controlled exchange coupling energy that oscillates as a function of the voltage. So if you apply this much voltage, you will induce a positive exchange coupling that will make the two magnets anti-parallel, or if you apply this much voltage, it will make them parallel because this is a negative exchange coupling energy. And this is all because of that quantum interference that I was talking about. So once you switch with the exchange coupling and remove the voltage, it will stay that way because the equilibrium value of your exchange coupling is 0. So you can switch in a non-volatile fashion. And bidirectional switching will be achieved for the same voltage polarity but different amplitude. So this is quite different from what people know. Based on this particular materials combination, we calculated that the current density at switching can be very low. So we assume cobalt iron boron as the magnet, magnesium oxide as the barrier, and ruthenium as the thin metallic spacer. And the current density can be 10 to the power 4 amp per centimeter square. Although this is a voltage control mechanism, we don't need current to switch it. But since this is a two-terminal device, when you apply a voltage, you also have a current. And the density is very small, where in STT it was around 10 to the power 7 amp per centimeter square. We can achieve 10 to the power 4 amp per centimeter square. And that translates into a much lower right energy because energy is I square R, proportional to the I square R. And we expect this new type of device to be here. The energy, we are expecting it to be slightly lower than embedded DRAM, and the device can be as fast as SRAM. Okay, another interesting thing is that now we also have a switching threshold, but now the threshold energy belongs to that exchange coupling energy. And the coupling energy depends on the anisotropy energy barrier of both of the magnets, but does not depend on the damping factor as I have shown for the spin transfer torque case. So this is interesting because the delay is still inversely proportional to the damping factor. So we can independently tune like both threshold and delay, where for the STT we have a trade-off. Okay, just let me quickly mention why this is like a parallel combination of two resistance. So this is like you're coupling two large energy with an exchange spring. So it's like two mass are coupled with a spring. And that's why the effective energy is just del 1 del 2 over del 1 plus del 2. So we need to overcome this effective energy to achieve the switching. Okay, so let me summarize. So we have talked about what challenges we have in technological advancement, especially in terms of memory density, speed, and how much energy consumes. And overall, like when you're talking about large scale data centers, the heat management is a major issue. And then I've discussed like how Spintronics have been, like what Spintronics have been doing from new materials translating into devices and applications to address some of these issues. Like it has been scaling the density in hard disk drives and presented a new type of fast random access memory. So currently this random access memory is like facing another limitation because right current is very high. So we need to figure out a way to lower the right current, either by looking into new materials or going into a voltage control devices. And I want to acknowledge so various parts of the results I have shown you was sponsored by various funding agencies. These two centers, this one ended, so this one I'm still part of this one. So they were both sponsored by SRC Semiconductor Research Corporation and DARPA, and also the last part of the talk was supported by NSF E3S Center. So before I finish, I just want to mention like what could be the research opportunities in Spintronics. So we are generating high volume of electronic data, and we need to compute that. And for compute, we have major components like memory, like energy associated with our integrated circuits, and the interconnects that connect all the elements. So we have opportunities in all of them. For example, memory, this magnetic memory is looking quite promising. Right now, the major drawback is the energy and on-off ratio. So right now, our MRAM exhibits 1 picojoule per bit, and on-off ratio is just 2 times the 200% magnetoresistance. But what we need to do, like do some research and bring it down to the femtojoule per bit region and enhance the on-off ratio like in the order what we observe for CMOS. And if we can do that, we can have a very dense memory technology based on magnetic memory. Another interesting thing is that this magnetic memory is already fast, and from Berkeley, like there are many reports on optical switching in the picosecond regime. But recently, from Berkeley, there was a report that with spin orbit torque, you can switch as fast as 2 picoseconds. So it's looking much promising. Like you can go beyond nanosecond. Other than that, many people are looking into spintronic energy harvester. So if you can have self-powered devices that can address some of the energy issues in like densely integrated circuits. And people are also looking into spin wave and magnon diffusion based interconnects, and that is supposed to be dissipationless and quite fast. And in the computation side, many people are looking into various things. For example, for classical computation, like people are talking about in-memory computation. There is a proposal of probabilistic computation from Purdue University. They're calling it PBIT. And then many people, so quantum computation is like a big thing right now. Many people are trying to use spin orbit materials to look for qubits. And there is a growing interest in topological materials for topological quantum computation. And Microsoft is actually very interested in this topic. So I'm pretty sure I have missed many other topics, but this is like a quick summary of what we can do in future. So with that, I would like to thank everyone for their attention, and I'm ready to take your questions.
Thank you very much, Shehrin Sayed, for the excellent talk. And although I'm not an expert by no means in this area, it was very like well said and very lucid presentation. So I'm sure everyone in the audience could understand the topics. So at this moment, I would like to invite the members of the audience to ask questions. So if anyone wants to ask anything, please go ahead.
Assalamu alaikum.
Walaikum assalam. Hi there. Please go ahead.
So, the concept of magnetic memory seems to me that we are changing the magnetic direction of the free layer with respect to the reference layer, and the device are Purdue have proposed using voltage control. They are using voltage, but my question is, what if the device is exposed to an external magnetic field? then will our data still be available then? What it will get removed?
Yeah, that's a good question. Yeah, if you apply an external field, definitely you will just destroy the data. But when people are making these like integrated circuits like these memory chips, they think about that and try to shield so that like any external perturbation do not affect much. So it requires some system level engineering to do that.
Thank you. Is there any other questions?
So does that answer your question?
Yes, sir.
Yeah, the floor is again open for discussion. So if anyone wants to add anything or ask more questions.
So that's another like I just want to make a quick comment. So that was an interesting question. So people are like looking into MRAM for another reason. Like it is supposed to be um, like robust against various radiation. And if you go to these magnetic conferences, I see people always talking about that, like for space applications. Like at space, you can be exposed to various radiation, and this magnet is like they're claiming that the magnet is supposed to be very robust against that. Just a quick comment.
That's fantastic. So I want to ask a question. So the effect that you're demonstrating, it's in room temperature, right? So um, do do you think that it would be possible to achieve room temperature quantum computing through magnetics? I mean, most of the research is right now done at a lower temperature. But what's your opinion
So
on that?
this effect,
Yes.
um, so for quantum computation, so like I'm still talking about a collection of spins, like which is inside the magnet. And when people talk about quantum computation in terms of spin, like it's just one spin, not a collection of spin.
Yes.
So yes, I don't have a direct answer. Like people do want to go to like room temperature for quantum computation, but still things are at very low temperature because the effect they are using that like people are using superconducting wires and other things. Like for example, some people are also using like S wave superconductor and connecting it to topological materials, and these
Mhm.
things take like very low temperature. Like these phenomena take very low temperature. So
Okay, I
this is I'm still talking about a macroscopic like spin view. So I don't think it can be
see.
applied to quantum computation.
Okay. So is there any other questions from the audience?
Assalamu alaikum. I would like to ask one question about
Yeah,
fabrication.
please go ahead.
For MTJ structure and STT structure, we see that we can apply a voltage externally. So my question is, if I want to apply the voltage, I need to make a contact pad with this tiny structure. So how can I make this contact pad and connect them with this MTT or STT junction, MTJ or STT junction structure?
How can you make?
The contact pad, like the MTJ and STT structure, you have shown that the IBM is a very tiny size, like it's nano dimension. So if I make this nano structure, I need to make a contact pad to connect with them. So how can I make the contact pad and connect with them to this structure?
Okay, yeah. So yeah, it's possible to make like these are like 50 nanometer diameter, and our lithography techniques are like quite advanced these days. Like you can make contacts and contact pads to these small junctions, and I am not the expert on how industry are doing, because they don't tell you what they are actually doing while making these chips. Like, these are all secrets. But in lab experiments, we, like, what we see, like, we work with a bigger thing, and it's possible, like, you can isolate with external like oxides and then etch it out and apply uh, bonding to that, and that goes to your contact pad.
Thank you.
Thank you very much. We have a written question from audience, so I'm going to read out the question. So Pallab Kumar Mitra asked, "Sir, is this for magnetization in memory recording in uh, Handy rule for zero position in memory, and dipole moment is for one position in memory recording in coupling in metal conductor? Here, noise is the problem."
Can you repeat? So let me just read it.
Yeah.
Hello, sir.
Yes.
Hello. Sir, there is a I show in this site. There is two metal is coupling position. They are for memory recording. That's for I thinking that's if we Hundi rules for opposite direction of electron flow. Is this for the zero position of recording system, or the memory empty system? And the dipole moment, that means the force of the electron is opposite direction of the magnetization. Is this for one that means the positive signal one, that's recording the signal of the memory storage system. Is this that is my question. This is this the prediction is right or wrong?
So which structure are you talking about? This one, the right one?
Coupling, yes sir.
The spin orbit coupling?
Yes sir.
So this is, so the Hund's rule. So that's
Holy
like,
rules means, sir, the electron flow in opposite direction. That means I assume that the position of the empty position of recorded value of that means null value of the recording system. That's like a recording of a tape, or the disc recording system, laser print. That's is the similarity or the difference is in this system. That's the
so I
thing.
might be missing something in your question. So because Hund's rule, like these type of things are like the atomistic picture. What
Yes,
I'm describing is like the electron transport in solid. So you know
yes,
the difference between solid, like one electron have multiple orbits, orbital, and there you can think those rules. But when you have solid, the electron
yes,
belongs to the whole group, and
yes,
I'm talking about collective phenomena. And the spin orbit coupling is a relativistic effect. It actually, this was like predicted back, like it was described in Einstein's 1905 paper, that like if you do, like if you modify the um, Maxwell's equations, like if you think about
yes.
in a relativistic way, like you can start seeing
Position or yes, sir.
all these exciting effects. But
Yes.
I clearly don't know how to think about Hund's rule in this picture.
That's means the opposite direction of electron flow in this graph. Okay, thank you, sir.
So it's actually coming from the electronic band structure.
Yes.
That that's my point.
Okay, sir. Thank you, sir.
Okay, so is there any other questions from the audience? Uh, if not, I don't see any questions in the chat box also. So let me quickly share my screen. So this is a we do this tradition of honoring our speakers virtually, and oops, wrong screen. So this is a virtual certificate of appreciation that is presented to Dr. Shehrin Sayed for giving this wonderful talk that can be a reference point for all who wants to work on magnetics and spintronics. So this is a wonderful talk, and also for the wonderful discussion session. So this is presented to Dr. Said for being the speaker at today's Meet the YP webinar.
Oh, thank you, Sajid Bhai.
You're welcome. And if there is no more questions or comments from the audience, I would like to thank everyone. Thanks to the speaker, and thanks to the audience members for staying with us in today's webinar.
Yeah, thanks everyone. It was like a great pleasure being here today. And thanks for the very interesting questions.
All right. Thank you. So with this, I would like to conclude today's session of Meet the YP.
So bye everyone. Stay safe.